Between Earth and Mars lies a void so massive that even light itself struggles to cross it quickly. Any operation we put on the Martian surface is bound by the inescapable speed limit of physics. This diagram illustrates the core constraint, a radio wave traveling between Earth and Mars. Depending on alignment, a one-way signal takes up to 22 minutes. Accounting for the return trip, that delay stretches up to 45 minutes. If a rover is about to drive into a crater, Earth won't see the telemetry until long after the chassis has hit the ground. On Earth, we build and test AI inside highly controlled environments. We rely on dense, climate-controlled server racks with virtually unlimited compute and instantaneous feedback. To communicate with distant planets, we rely on infrastructure like the Deep Space Network. These massive satellite dishes transmit data across millions of miles, but they operate through narrow contact windows, limited bandwidth, and frequent outages caused by solar geometry. Down on the Martian surface, the constraints multiply. There is no existing power grid. Every watt-hour, every GPU cycle, and every kilogram of computing hardware must be painstakingly managed. Distance and energy scarcity turn every standard networking assumption into a cyber-physical hazard. If a large software update saturates a router, a delayed stop command could cause a catastrophic collision. Mars cannot be operated like a distant data center. A viable architecture requires local autonomy that senses, decides, and survives on its own, syncing state changes with Earth only when physics allow. Pushing massive frontier machine learning models out to a delayed, harsh environment requires a structured operating fabric designed specifically for local-first execution. The proposed architectural solution is a deterministic control overlay, known as the Tensor Network's Mars Habitat Control Plane, or PTCP. This diagram shows the PTCP control overlay sitting above standard delay-tolerant networking substrates. It's divided into 4 modules: AI Factory for compute allocation, Sarah AI for physical safety, Zero Day for topology defense, and ACSO for governance. Earth handles the heavy lifting of training and simulating models. Mars takes those bounded models to operate independently, guaranteeing that the mission survives even when the connection inevitably drops. The baseline standard for deep space communication is Bundle Protocol version 7, defined in RFC 9171. It operates on store, carry, forward semantics. Data is broken into discrete bundles that wait in local storage until the next network link becomes available, allowing information to hop slowly across intermittent links. While this guarantees data eventually arrives, blind delivery consumes critical power budgets. Transferring massive, low-priority files during a power shortage actively endangers the habitat. This is where the first layer of the PTCP overlay, the AI Factory, intervenes. The AI Factory routes data packets across the settlement, scoring traffic against an energy grid and prioritizing paths by useful work per joule. As the microgrid margin drops to red, it halts non-critical transfers, ensuring priority model updates execute. This layer dynamically manages heavy Mars-specific workloads, sorting terrain world models, hardware-in-the-loop simulations, and mission-critical reasoning against tight thermal constraints. Raw throughput is meaningless under these conditions. A safety inference that arrives late, or an energy-draining download that triggers a blackout, is a total mission failure. When software dictates the movement of heavy machinery, network latency directly controls physical safety. Consider an autonomous rover swarm encountering an unexpected hazard. The vehicles instinctively attempt to send high-resolution bulk imagery of the threat back to the habitat. This sudden surge in raw sensor data saturates the local network queues. A critical, lightweight, safe stop command can easily become trapped behind gigabytes of non-urgent media. The second PTCP layer, Sarah AI, prevents these queue collapses. Sarah AI decouples the network into a split pipeline. Massive bulk imagery blocks are forced down a slower path. A dedicated fast path remains reserved for metadata. High-value data, like emergency stops, travel exclusively down this fast path, ensuring vehicles halt instantly despite background traffic. This enforces an autonomy ladder, ensuring that low-level physical reflexes and hard interlocks operate deterministically. By reframing physical action as a strict network control problem, critical safety envelopes remain mathematically predictable and entirely outside the complex reasoning models. Inspecting encrypted payloads for malicious code is computationally expensive and nearly impossible across highly intermittent space links. The third layer, PTCP 0-day, provides local defense without relying on deep packet inspection. A node map compares an approved pattern of life against a deformed network geometry. 0-day monitors who communicates with whom and across which boundaries. It calculates a deviation score, D-topo. As communication drifts from the baseline, nodes glow red, indicating rising risk. Before a security signature is even available, 0-day executes a staged containment response. It automatically rate limits suspicious traffic, requires stronger identity checks, or physically isolates the compromised nodes. This operates under a strict fail operational safety rule. Containment protocols are prohibited from blindly powering off essential life support, braking, or emergency communications. A Martian defense in-depth stack isolates threats using network structure alone, explicitly preserving pre-engineered degraded operational modes so the settlement survives the quarantine. Mars must act autonomously to survive, which creates a severe governance challenge. Earth must retain executive authority without becoming an operational bottleneck. The final layer, ACISO, acts as the executive control layer and maintains a living digital twin of the mission. Earth dictates governance by pushing versioned policy deltas to Mars, creating boundary boxes that limit local agents. Any new capability clears a strict update machine. A model artifact moves linearly through 5 rigid gates: received, attested, shadow, bounded, and active, before interfacing with a physical actuator. After Mars executes operations and survives the immediate physical reality, the system generates cryptographic evidence deltas, detailing exactly why decisions were made, sending this data back to Earth. If Earth's policy and the settlement's local conditions disagree, the conflict rule is absolute. The immediate Martian physical safety state always wins locally, while differences are merely recorded. Trust is defined, actions are staged by authority, and cryptographic provenance is preserved entirely, creating a versioned state model that Earth can audit asynchronously. Viewing the complete proposed interplanetary stack here, we see exactly how compute, safety, defense, and governance unite efficiently over the underlying delay-tolerant network substrate. This architecture strictly enforces 4 deployment invariants. First, no unsigned software model is ever permitted to reach a physical actuator. Second, every single update deployed to the planet must carry a verifiable predecessor and an immediate automated rollback path. Third, physical interlocks and hardware safety envelopes must operate completely independently, stationed strictly outside the machine learning model. Finally, cryptographic evidence of all local autonomous decisions must survive any network partition, so it can be fully reconciled with Earth later. Securing a permanent foothold on another planet relies on auditable, local machines operating safely within explicit physical and cryptographic boundaries.